दे रहा है? You know, compared to US, यहाँ के पंखे बड़े तेज चलते हैं, ऐसा लगता है टेक ऑफ होने वाला है. Okay. All right, folks, let's get started. This is the last day of our short course, and we will be done by about middle of the day. So today I will, in this lecture, talk about thermal management of lithium-ion cells and battery packs. So far, we have been sort of looking at the science of lithium-ion batteries. In this lecture, I will talk a little more about the engineering, thermal engineering of batteries. In other words, the question is, how do we cool a cell or a battery pack? That's the main question. A secondary question also is, how do we heat a cell or a battery pack? About 90% of the times we are worried about the cell getting too hot and then a need to cool it down. But sometimes there is also a need to heat up the cell. If you have an electric car and you need to operate at very cold temperatures, then to start your car, you have to first heat up your battery pack. So we are worried about both heating and cooling of the battery pack, and that's what I will talk about today. Okay. The need for cooling something is not new. If you look at the evolution of thermal engineering, we have over the past several decades worried about cooling of a variety of other engineering systems as well. Okay, the one that I am most familiar with is the cooling of computer chips. Dr. Chandar, who gave a very nice lecture on this, has a career built on the cooling of computer chips. So what happens in computer chips is that the little chip inside the cell phone or the computer generates a lot of heat, and that heat has to be removed in order for it to work, right? And so in the past 30-40 years, there's been a lot of research on the cooling of computer chips, and it turns out that a lot of lessons that we have learned from there can be used for the cooling of lithium-ion cells as well. Okay, so I want to talk briefly about what are the unique features of thermal management for lithium-ion cells. There are a few unique challenges that exist in the cooling of lithium-ion cells that I want everyone to be aware of. So the first thing is that oftentimes weight or volume is an important challenge, right? If I have an electric car that has a big battery pack that needs to be cooled, then I don't want to add to the weight of the car because of the thermal management technique, right? So for example, if I have a pack containing a bunch of lithium-ion cells and I decide that I'm going to cool it with liquid water or let's say air, if I'm going to blow air over it, then I need a fan, I perhaps need a filter, and I need several other equipment in order to make this work. Each of those things will have a weight and a volume, right? When I design an electric car, weight and volume are both limited. And the same problem also exists in a bunch of other applications of lithium-ion cells like spacecraft and consumer electronic devices and so on and so forth. The second consideration is that of power. This fan, which will blow air over it, will consume power. Where will that power come from? It will probably come from the cells themselves, right? So what that means is that I now have lesser power available to do the job that I really want to do, which is to move the car, right? So what percentage of my energy stored will be used up simply for cooling the cell is an important parameter that I want to track, and that number should not be more than maybe a few percent at most. If say 25% of this power is being used for just for cooling it, then that's not ideal at all. Okay, so weight and volume, power, and a practical consideration also is that of cost. So I think these are the top 3 practical considerations in designing a thermal management solution. In addition to that, as far as the characteristics of this are concerned, we talk in terms of delta T. I don't want to call it delta T. Temperature reduction per unit power is an important metric for any thermal management technique. In other words, for every 1 watt of power consumed by the pump or whatever other equipment that I am using, how much is the reduction in the peak temperature that I am able to get. This is sort of like what I get divided by what I need to pay to get it, right? So whenever we design or evaluate a thermal management system, this is a parameter that I want to track, and I want to make sure it is as high as possible. Then in addition to that, in the world of lithium ion cells, one very specific consideration is delta T, which is the temperature difference across the cell or the pack. In other words, going back to the previous slide, if I cool down this battery pack by blowing air over it, then the peak temperature in this battery pack will probably occur somewhere here, right? And the minimum temperature will probably occur somewhere here. The difference between the two is the temperature difference across the pack, and that temperature difference needs to be minimized. In other words, not only am I interested in reducing the temperature of the entire battery pack, but in addition, I also would like, if possible, for the battery pack to be as uniform as I can make it. Because if I am cooling down this cell very much and not this cell, then these two cells will age differently. One of them will age faster than the other. The one that is not being cooled very well will age much faster than the other cells. And it turns out, like in life, that the performance of the entire pack is determined by the weakest link in the system, right? And therefore, I would very much like for all these cells to age as uniformly as I possibly can. This in fact applies even for a single cell. So if I have a single cell, and if I'm cooling it by blowing air over it, then clearly the peak temperature in this cell will occur here, and perhaps the lowest temperature will be here. This temperature difference I would like very much to be as low as possible. In the past decade or so, the research field of thermal management of lithium ion cells has really taken off. There are literally hundreds of papers on how to cool down lithium ion cells. What has basically happened is that a bunch of people that have expertise in thermal management in general have identified lithium ion cells as an interesting system, and said, okay, I know how to use heat pipes for thermal management systems, let me use heat pipes for cells. Somebody else says, okay, I know how to use evaporative cooling, let me show how to use evaporative cooling for lithium ion cells, and so on and so forth. Okay, this still continues, in my opinion, to be a rich area in which to do work, because I don't think all the problems have been solved yet. We still do not know a lot of things about thermal management of cells, and any creative ideas about the cooling of cells is taken very positively in the research community. So if you guys have any ideas, any thoughts about cooling of cells, go forth and explore. What I will do is that I will list out a number of different techniques that I have seen on the cooling of cells, and in fact, let me see if I can. Where do I go? No, not this one. So this paper that just got published, some collaborators from China and I wrote a review paper on indirect liquid cooling of lithium ion cells. It's a good paper, it's a long paper, 31 pages, but I think it does a very good job of summarizing the literature on air cooling, liquid cooling, phase change cooling, heat pipe cooling, etc. And it gives lots of different examples of different types of work that people have done. So if you are interested in thermal management of cells, this is a paper that you might benefit reading from. What I like about it is that it is very comprehensive. Lots of figures and stuff, and lot of in-depth discussion of what others have done. And it has like 200 or so references in the end. 179 references. Okay. So this is the paper, just came out. Yeah. Let me go back here and make a list of different approaches for thermal management of lithium ion cells. The most common approach is air cooling. Why? Because air cooling is cheap, air is commonly available, all you really need is sort of a fan, right? So there is a lot of papers on air cooling of lithium ion cells. The other common technique is liquid cooling. In some sense, the literature in thermal management of lithium ion cells has followed the same path as computer chips. When computer chips started getting hot in the 90s, the first approach was to use air cooling. And then when people figured out that air cooling is not going to be sufficient is when they moved on to liquid cooling and then evaporative cooling and other more advanced techniques. Sort of the same thing is happening in the field of lithium ion cells as well. Air cooling is the fundamental, easiest, cheapest, but it has its own limits. So then the next one is liquid cooling. Within liquid cooling, the most common liquid coolant used is water. But a key disadvantage of water is that water cannot make direct contact with your cells. You can blow air over your cells, sure, but you cannot blow water over the cells because the water is going to short your cells. So almost always there needs to be a sort of like the cooling has to be indirect. There has to be a thin sheet of something that separates the water and the battery pack that you're trying to cool. Okay? But nevertheless, water has very high heat capacity and reasonable thermal conductivity, and therefore the performance of liquid cooling is certainly better than air cooling. The cost that it comes with is greater weight and greater volume, because with air you can always cool the pack and then reject the air into the surroundings, right? Because there's lots of air around. But with water you have to design a closed loop system where the water that you use for cooling the cells comes out of the pack, then that water itself has to be cooled down. So there needs to be a secondary heat exchanger so that you can then take the same water and circulate it around in a loop. So then you need a pump, you need good piping, you need another heat exchanger, and it just becomes a lot more complicated. And in the context of an electric car, any system that you design needs to be able to run for at least 10 or 15 years. So reliability becomes an important question. Any one of these parts that fails can fail the entire electric vehicle. Okay? In this context, immersion cooling has also been looked at in a lot of detail, and I'll show an example shortly. The basic idea being that with water, since you cannot directly flow over the cell, therefore there is always a thermal resistance between the cell and the water. Whatever you put on top of the cell or the pack offers a thermal resistance, and that reduces the performance of thermal management. And therefore there is motivation in taking some sort of a liquid and being able to flow that liquid directly on the cell or the battery pack. And if you want to do that, the most important property of the liquid is that that liquid should not conduct electricity. Because if it is flowing right above or on the cells and all the wiring, etc., then any short will just kill your battery pack. So this needs dielectric liquids. Fortunately, dielectric liquids are not new. Dielectric liquids have been used for the cooling of at least two other systems that I am aware of. One is computer chips. So there are papers out there on taking a computer chip and instead of cooling it with a heat sink or a fan, blowing this dielectric liquid over it directly. The dielectric liquid can touch all the wires and connections and everything without causing a short. There are some very well known dielectric liquids. The one I am most familiar with is called FC72. You can easily go and buy FC72 and get started. It's not very expensive either. Okay. The other area in which dielectric liquids have been used for cooling is transformers. High power transformers actually sit in a bath of oil that is circulated and it is cooled on a continuous basis using immersion cooling. Okay. In addition to air cooling and liquid cooling, some other techniques that I have seen in the literature include heat pipe cooling. And I will show an example of this in a paper from our lab. Heat pipes are also not new. See, none of this is new. All of these techniques have already been used in other cooling problems. All we are doing here is to adapt these for the cooling of a new system, the lithium ion cell, and modify it to sort of cover the quirks of the lithium ion cell and so on and so forth. Okay. In addition to heat pipes, I think the last major one is phase change cooling. Within this, there are two categories. One is liquid to solid. Oops, sorry. One is liquid to solid, and the other is liquid to vapor, meaning melting and solidification or condensation and evaporation. The basic idea is that if the process of melting requires energy. So if you have a lithium ion cell and if you put a bunch of wax, solid wax around it, then that wax is capable of absorbing heat from the cell and melting, and in the process it is able to take up a lot of heat from the cell and cool it down. Similarly, if you surround the cell with a film of liquid, then as the cell gets hot, that liquid film will evaporate and as it evaporates, it will absorb a bunch of heat from the cell. In both cases, we will see some cooling of the cell. This melting has been looked at in a lot of detail. There are again literally hundreds of papers on phase change cooling of lithium ion cells. People have used this PCM, that PCM, this configuration, that configuration. That field is quite rich. I think the area that still has not seen a lot of work is evaporative cooling. In other words, can I have a film of liquid around my cell which absorbs heat from the cell and evaporates, and as a result takes away a bunch of heat from the cell? What are the reasons why this has not been done much? I think one, because most dielectric liquids have very high boiling points. So if I put if I put a layer of FC72 around my cell, then that FC72 will simply not evaporate until the temperature rises to the boiling point of FC72, which is probably very high, right? So on the other hand, water will begin to evaporate at 100 degrees C, right? And if I adjust the pressure of the water, then I can make it evaporate at a lower temperature as well, but water is not dielectric. So in other words, in order for this to work, we probably need a combination that combines the dielectric nature of the liquid with a low melting point. So if you are aware of a low melting point dielectric liquid, then that would be perfect for the kind of evaporative cooling we are talking about. I think my opinion is that within this crowded space, the one niche area that has not seen a great deal of work is probably this. Both experimentally and from a theory or simulations point of view. Perhaps just a measurement of evaporative cooling and its comparison with other cooling techniques will make for a great paper. All right. Any questions or thoughts so far? What, evaporative cooling? Sure, it will. So what do we need? Let's think about it. Say I have a lithium ion cell and I want to do evaporative cooling of the cell. What do I need? How will this happen? Sure, yes. So we might need, I don't want to surround it with a lot of liquid. I'm not trying to do bulk evaporation. I'm only trying to do evaporation on the surface. So what I probably want to do is to have a spray which will spray this with a thin film of liquid, right? And then I need to worry about hydrophobicity and hydrophilicity of the liquid, right? The liquid has to adhere to the surface of the cell and create a thin film. Do you see what I'm saying? And then as the cell heats up, this is going to evaporate. And surrounding all of this, I need some mechanism to collect that vapor, because I don't want it to escape into the atmosphere. I don't have an infinite supply of the coolant, right? So all of this needs to be collected and pumped back into the spray. Yes, I agree that all of this will increase the weight and volume of the system, and it will also require some power. How much and how does that compare with the other techniques that we've talked about here? I do not know. That, I think, is precisely the work that needs to be done, right? A comparison of the performance of evaporative cooling versus other cooling techniques. Did you have a question? Sorry?
Regarding immersion cooling.
Yes.
Still available for the research.
I'm gonna talk about immersion cooling in a lot of detail. Yes. So for the rest of this lecture, what I would like to do is to take up 3 of these topics that I have listed here, in which we have made some contributions, and open those papers and discuss those in detail. So air cooling, heat pipe cooling, and immersion cooling. Yes. Yes. Possibly, I have seen that. Yes. Yeah. So the spray is just sitting there. It's not operating continuously, but whenever a temperature sensor says that, look, I'm getting too hot, it just sprays it and just for a little bit cools it down. Absolutely, that is certainly possible. Just a last ditch safety measure. Sure, absolutely. So our lab has sort of been focused more on the fundamentals of heat transfer in cells, and honestly we've not really done a lot of work in thermal management, but here and there we have contributed in a few different fields, and so I'm going to talk about each one of them. Which one shall we start with? Let's start with immersion cooling. Why not? So this was a paper by Swapnil Salvi, who was a master's student here with Dr. Tyagi, and then he came to my lab. Very nice fellow, very easy to work with, and very friendly. So he went to Southwest Research Institute, which is a private research company in San Antonio, Texas. He spent a summer there, and then after he finished his PhD, he went back there full time. Funny thing is, when he was interviewing for a full-time position, I asked him how was your interview. He smiled at me and said, Dr. Jain, it was cool. It was just a reunion. He knew all the people already because he had done a summer internship there, and so it was more or less a formality for him to go there after his full-time position. So what he was interested in and what the company was interested in was how to carry out immersion cooling of a battery pack of lithium ion cells. So as I have said, immersion cooling means that you take the cell and you basically immerse it in a dielectric fluid, and then you pump that fluid in and out, sort of like a heat exchanger, in order to remove heat from the cell or the battery pack. At this time, this was 2022 or 23, is when all of this happened, during the COVID time. And at that time, since then, there's actually been a lot of other papers on immersion cooling as well. But I'm presenting this since I'm most familiar with the details of this work. So let me just show you the setup that he had put together. I'll come to that in a moment. Let me show you this first. So this is a picture of his test rig. It's sort of difficult to see the details here, so let's take a look at the schematic instead. What he has is a pack of 7 cells that are put together. So it's a fairly small battery pack. The typical battery pack of a lithium ion of an electric car has thousands of cells. So this is a reasonably small battery pack. It's a module, exactly. They are all connected to each other through bus bars, and then he puts it in a test rig with an inlet and an outlet. You can sort of see the test rig here, and through this inlet and outlet he can blow or pump dielectric liquid in and out, thereby cooling the cell. Of course, these cells are also electrically connected to the outside world so that I can charge and discharge the cell at any rate I desire. And the outer setup looks like the following, where these are my cells, this is my test rig, and there are thermocouples and flow control valves and flow meters and an external heat exchanger. This dielectric fluid that comes out gets hot and needs to be cooled down before you pump it back. So there is an external heat exchanger, after which it goes back into the test rig. So this was sort of the measurement that he had done. It's not a straightforward setup. It took him probably the entire summer to set it all up. What he found was very interesting. If he found that by comparing the temperature of the cells with and without immersion cooling, it was clear as expected that the temperature of the cell goes down as a result of immersion cooling. What was more surprising was that it turns out that immersion cooling of the cells caused a reduction in the electrochemical performance of the cells. So he carried out measurements of the cell capacity. So he took this setup of cells being immersion cooled, and he ran this setup through multiple cycles of charge and discharge, perhaps thousands of cycles if I remember correctly. Over his entire experiment ran 28 days. So over 28 days the cells were being charged and discharged and charged and discharged, sort of like that figure that we just saw. Yeah, so this was just discharge, rest, charge, discharge. So the cell is going up and down, up and down, up and down all the time. This is plotted for 1 RPT, 24 hours, right? He had done this for 10 RPTs for about 10 days or some such long period. And he found that as time passes, there is a reduction in the capacity of the cell as expected. However, the reduction in the capacity of immersion cooled cells was slightly larger than baseline cells that were not being immersion cooled. So our hypothesis was that what is basically happening is that the immersion cooling is working too well. In other words, it is cooling the outer surface of the cell so much that there is a temperature gradient within the cell. The core of the cell is much hotter now than the outside of the cell, because of which it is well known that a temperature gradient in the cell causes greater capacity fade in the cell. So while immersion cooling is good for thermal management, we found that we still need to tune it in order to minimize these. It's not a great effect, it's only maybe 1% additional capacity fade, but nevertheless this needs to be understood fundamentally, and one may need to design the thermal management system to minimize this undesirable effect. So the rest of the paper was simply on running a bunch of experiments to try and understand how, to try and understand the mechanisms behind this capacity fade. Some of the electrochemical work that he had done, I myself don't understand fully. But to help with that, he also ran numerical simulations of the immersion cooling process. This is fairly straightforward. Yes.
In the base case,
Yes.
the temperature that I'm expecting, is it at the center?
No.
Going to be higher compared to the first cooling?
Yes. Yes. Absolutely. So, let me draw it here. So, without cooling, I expect the max temperature to be here and the min temperature to be here. They are both quite high. Okay. With cooling, they will both come down. But the min temperature will come down so much that this temperature gradient goes up. And that is not desirable. Some people will argue that this scenario is worse than this scenario. They will say, can you do something so that the core cools down and the surface doesn't cool down? It's okay if the surface doesn't cool down at all. That is better than the surface cooling down too much. Because the temperature gradient within the cell causes non-uniform aging of the cell. And that's not good for the health of the cell. The aging of the cell is temperature dependent. And in this case, the core of the cell will age much faster than the surface of the cell or the outer regions of the cell, and that causes an imbalance in the electrochemical performance of the cell.
So let's say the cell is made of a gel.
Yes,
So in some way, a cell is not a single bed, bed cell.
Yes.
We have some multiple cells in some way.
In some way, yes. Yes,
There are multiple.
correct,
So in that way, it consists of various of cells.
correct.
So now I'm saying I have two scenarios. In one, I have the one cell, which
Yes.
is a subcell, which is at the center is getting reduced faster.
Yes.
Then also it will be better than the other case where they are not able to.
Well, so I don't know the electrochemical reasons behind it, but what they say is that the deterioration of the cell should be as spatially uniform as possible. I don't want one part of the cell deteriorating much faster than the other. I don't know. I don't know the details myself.
The addition will be better. Like
Right.
how much total addition of the capacity there.
Yes.
But even if the whole one is totally damaged in some way.
Yes.
Like let's say there are 10 subcells.
Yes.
First, the core and the center is totally damaged.
Yes.
But if 9 are performing well, I
Yeah.
will expect only 10% reduction in the
No, but
capacity.
the argument that I've heard is that the weakest link in the system determines the performance of the system. Sort of.
Will the part of it
Is worse. Yes.
deteriorate, then the other part will not be worse. Because it's a completely thin and
Somehow, yeah. I don't know. I don't know. Yes.
So, will it be different for a prismatic and the electrical cell?
No, this principle applies in general.
Prismatic cell
In prismatic cells also, the temperature gradient within the cell is important and should be minimized. However, if I think of a prismatic cell versus a circular cell, cylindrical cell, because of the poor thermal conductivity, the temperature gradient is expected to be larger for the cylindrical cell than for a thin prismatic cell. Right? A thin prismatic cell, the thermal resistance within the cell is very small. And therefore, this non-uniform cooling problem is particularly relevant for cylindrical cells. And from that point of view, one rule of thumb is that your cylindrical cell should not be very large. The radius of the cell should be as small as possible. Much better to have a larger number of smaller cells than to have one big hunk of a cell. Yes,
Right with the changing of orientation.
we have not. No, this was all done in one.
There will be some effect if we change the orientation.
You mean gravity?
Yeah.
Yes, sure, perhaps, but keep in mind that this is all forced convection cooling. This is not free convection. So why will gravity play a role?
And one more thing, that why we want to go for force cooling? We can create a system in which the fluid can flow.
Yeah, but as you know, forced convection is much more effective than natural convection. So if I stop blowing, if I stop pumping this coolant, then there will still be some circulation because of buoyancy within this, and there will still be some cooling, but that cooling will be very, very little compared to forced convection. If I was to see, um, if I was to have in this test rig my cells, if these are surrounded with a liquid and I'm not circulating the liquid, then not a lot of heat will be removed, right? What I can certainly do is that I can control the flow rate through my pump to blow only or to pump only as much coolant as I really need to cool it down. That I can certainly do. But I probably don't want to make it zero. If I make it completely zero, then I will not have good cooling at all. Okay? Yes. Yes, it is the maximum temperature in the pack minus the minimum temperature in the pack. That's the delta T. Yes, so this is the top ones are max temperatures and the bottom ones are min temperatures. And the three cases that I have drawn, one is baseline, second is immersion cooling, and the third is what I will call as ideal immersion cooling. Okay? We have learned in previous lectures that the thermal conductivity of a lithium ion cell is very poor, 0.2 watt per meter Kelvin or so, right? And therefore, this problem of temperature gradient inside the cell is inevitable. There will always be a temperature difference between the core of the cell and the outside surface of the cell. The only way to prevent it, the only way to prevent this temperature difference is to directly cool the core of the cell. Anything that I do to cool the cell on the outer surface will cool the outer surface effectively and will not cool the core of the cell effectively. That gives us a motivation to investigate how we can possibly cool the core of the cell directly. The simplest approach for that is to make an annular cell. Imagine if I have a cell with a tiny little hole in it through which I can blow air. That way, there is some air blowing on the top that cools the outside. There's some air blowing through the annular hole that cools the inside, and I'm getting the best of both the worlds, right? Unfortunately, before people realize that, the manufacturing infrastructure for these cells had already been figured out to build a solid cell. And so now it is very, very difficult to go to a manufacturer and say, can you please redesign your manufacturing in order to have a hole in the middle of the cell? It is too disruptive for manufacturing. Keep in mind that these cells need to be hermetically sealed because the electrolyte cannot evaporate. And so you have to redesign the whole cell in order to be able to provide a hole in the center of the cell. Nevertheless, we have tried this out in our lab just to see what the impact of this is going to be. So, since we did not have a cell with a hole, we made a hole in the cell and inserted a heat pipe to see what happens to the thermal performance of the cell. Okay, so that is the next paper that I want to talk about, and that is Dean Anthony, who was a master's student in our lab. He was a physics teacher, a high school physics teacher, who for whatever reason decided that I want to go back to school and get a master's degree. And so he came to our department, and very interesting, very nice guy. I met him 6 or 7 months ago. He's doing very well after finishing his master's. Huh? Now he works for a defense company called Northrop Grumman. It's an aerospace defense company, and he cannot tell me exactly what he does. Huh? No, he did not go back to. He wanted to get out of it, essentially, and he thought of this getting a master's degree as his ticket out of high school. Yeah, he does something to do with satellites and the trajectory of satellites and all that stuff. Nothing to do with batteries, by the way. A lot of my students, having contributed to a lot of our work on batteries, are no longer actually doing batteries, right? And I'm quite sure that I'm also going to go and do other things in my life. I'm not going to do batteries all the time. My focus is already shifted to other more fundamental questions, and I think that is the fun of academia. Through students like you guys, we are able to shift directions and identify new interesting problems to work on, and you know, have an interesting life, not monotonous. And the other two authors on this paper, Derek Wong and David Betts, were our collaborators in the electrical engineering department, who knew a lot about the electrical aspects of batteries. So here is a cell that we purchase from wherever. We basically drill a hole in the center of the cap of the cell to be able to insert a thin heat pipe into the cell. One challenge was that this cell, I think, is an it's a 26650 cell, so its diameter is about 26 millimeters, maybe about this much. I want to drill a hole in the center and insert a heat pipe. This heat pipe needs to be very small, right? I don't want the heat pipe to be occupying 50% of the volume of the cell itself, right? Then what is the point? Then the capacity of the cell will go down so much that I will not have an effective cell. So we needed to find very thin heat pipes, and that is where a friend of mine from China helped. He runs a heat pipe company in China, and he donated to us a bunch of really thin, I think these were 2 mm or 3 mm heat pipes that he makes for some client, and he was just happy to give it to me like candy. And so we drilled a hole, we inserted a heat pipe along with a thermocouple wire on the heat pipe body, because we wanted to measure the core temperature as well. And then we put some sort of an epoxy sealant around it and connected it for electrical connections and all that stuff. And our success rate for doing all this was about 30%. So we tried this on 3 cells, 2 of them immediately die, because the process of drilling a hole in the cell, inserting a heat pipe, etc., will cause some sort of a short somewhere, and the cell does not work anymore. One of the cells survived. All the measurements were done in a hurry on those cells. I think Dean did not go back home that night, and because the cell was also slowly dying, no matter how well you seal it here, we don't have manufacturing level precision for sealing, and therefore the electrolyte will begin to evaporate and the cell will die within a few days. So we were in a hurry and we wanted to take all the measurements we wanted before that happened. So I remember, before we committed to drilling a hole, we already knew from some past measurements that this is not going to stay with us for a long time. So we already had a plan, all the equipment was in place, we knew exactly what measurements were needed in order to make a nice paper, and then it was execution time. As soon as it was made, we tested it out in David's lab, and when he said the cell is okay, we just went and did a bunch of measurements before the cell went away. So remember, what was the motivation of this? The motivation of this was to cool down the core of the cell, right? The outside part of the cell is easy to cool. I'm not too worried about that. I'm worried about the core of the cell that needs cooling. And it turns out, as expected, that we got some very nice results. First of all, we carried out electrochemical characterization of the cell. So we carried out a voltage versus time measurement, and we carried out an EIS, electrochemical impedance spectroscopy. It's basically a measurement of the health of the cell, the key characteristics of the cell, sort of like its blood pressure, its temperature, etc. And we show that uh, red is the control cell, blue is the heat pipe cell, the cell with the heat pipe, and the two of them are fairly similar to each other. There were some differences in the EIS, which David and his student were able to explain. They had a better idea of what EIS means and so on. By the way, we have always benefited from good collaborations. We don't know everything. There are others who have a particular expertise in some other field, and I've always found that it's very helpful to shake hands and work with somebody who has a complementary expertise. So you all should not hesitate to try and find those collaborations. If there is something that you don't know very well, is there somebody else in your institute or even outside who can help you with that? Trust me, people are always looking for such collaborations themselves. And creating teams like this is really what leads to good, solid work. Then we carried out temperature measurements. And so this is measurement of the core of temperature at the core of the cell. Red is without heat pipe. Yellow is with the heat pipe, but the heat pipe is inactive. In other words, let me just draw it here or here. Here is my cell. Here is the heat pipe inside the cell. The heat is going to go up through the cell. But in order to actually remove the heat, I also need to blow air over the tip of the cell. If I don't blow air over the tip of the cell, then having a heat pipe is meaningless. And that is actually what the yellow curve was. So even without any air blowing over the cell, I still got some decent benefit in the core temperature. And when I started blowing air over it, there was even more benefit in the cooling of the cell. And then we looked at the effect of the speed of the fan, and as expected, the more air I blow over it, the more cooling I get. As you can see, this is sort of applied work. We are sort of trying to see how things will happen in real life, right? There are no equations here. There's no basic science here. Yes? This was all happening at 20 amps discharge. And I think this was a cell, the cell capacity, let's see. I think it was about 2 amps or something like that. Two amp hour cell, 2.8 amp hour cell. So the C rate was about 10C, 7C or something like that. 7C is an extremely high discharge rate. Yes, we are looking at 20 amps of current. How many amps of current will kill you? If you're going to do research in this field, please before that find the answer to this question. How many amps of current will kill you? I think a few amps of current is a lot of current, right? Typically in electrical measurements in the lab, usual measurements, we talk about maybe 1 amp at most. This is 20 amps of current. It's a lot of current. Please be careful. Yes?
What is the liquid inside the heat pipe?
I don't know. My friend from China was the one who gave me the heat pipes. The heat pipes were sealed, and we never bothered to ask or find out what was inside. It was probably a secret sauce that he does not tell anyone. Any other questions on this? So then we were also interested in, as we said, understanding the temperature difference between the outside and the inside. So here is a plot of that. Why don't we focus on part B specifically? So part B plots the temperature difference between the inside and the outside as a function of time while I charge and discharge my cell. Okay, the red is the baseline, the insulated heat pipe. You can see that there is a significant temperature difference between the inside and the outside, 12 degrees C. The usual recommendation is not to exceed 5. So at about 7 C discharge rate, we are blowing through that recommendation. But on the other hand, if you look at the other curve, in the presence of the heat pipe, the temperature difference between the outside and the inside stays pretty close to 0. And in fact, somewhere towards the end, it even becomes negative. Becoming negative means that the core of the cell is actually cooler than the outside of the cell, which is very unintuitive. It can only be explained on the basis of the presence of the heat pipe. The heat pipe is doing such an excellent job that it has turned the problem on its head. We used to be worried about the core being hotter than the outside. Now what has happened here is that the outside is slightly hotter than even the inside of the cell. So this sort of provided us a proof of concept that inserting a heat pipe into a cell can be extremely beneficial in removing heat from the core of the cell. A lot of people talk about this temperature difference within the cell and how the core of the cell is not being cooled very well. Here is a technique to do that. The only problem here is that our experimental setup was very crude. Drilling a hole in a cell and inserting a heat pipe is not the way it should be done. The manufacturer should take the heat pipe and should insert it into the cell during the manufacturing process. Remember we said about those electrode layers being rolled around a mandrel in order to create the jelly roll. Exactly. The mandrel in usual manufacturing is actually withdrawn at the end. And we make a simple argument, why not make the heat pipe the mandrel itself and never let it out, just keep it there. It can possibly short, yeah. So those are things that one will have to figure out. A thin insulating film on top of the copper heat pipe will not hurt its performance too much, and it might perhaps provide the kind of insulation you're looking for. Also keep in mind that this heat pipe will have to come through the cap of the cell. So the cap and all the other safety features we talked about under the cap will all need to be redesigned. They're typically located in the center of the cap, and therefore they would need to be moved out, and you would have to provide a hole in the cap through which the heat pipe can come out, and then you would have to provide some sort of sealing around the heat pipe in order to make this work. And of course, for all of this to work, cost is also an important consideration. If I have a lithium ion battery pack for an electric car that has 10,000 cells, then I cannot possibly have 10,000 heat pipes.
What is the price of that heat pipe?
For us it was priceless because there was no manufacturer in the world who was able to manufacture at that time, this is 2016 or so, a 2 millimeter diameter heat pipe. My friend said, yes, I make it, I'll give it to you, how many do you want? A typical heat pipe of a more regular size costs of the order of $50 or so. If I purchase a few of them. If I am a manufacturer who's going to purchase 1 million of them, then I will get bulk pricing and it will be lower.
50%.
Yes.
Then the price of cell in India is around 500 or 700.
Yes.
The
Heat pipe is more expensive than the cell. Yes, absolutely. Yes. You know, that is not necessarily a reason to stop working on this, right? We don't worry about cost as much because when things begin to happen in bulk, the cost does come down. The cost of batteries also 15 years ago was much higher, right? And the expectation is that as the world adopts a technology, the price does come down.
generally manufacturer does not want to imply at current time that it can increase the who will purchase the cell.
Yes, absolutely, absolutely. Any other questions? So, I think that is all that we had said in this paper. And I think this is also a good one to look at. This is temperature rise versus time for different currents. So, sorry? For the same cell with and without heat pipe. So solid line is without heat pipe, dashed line is with heat pipe, and the colors represent the 5 different currents at which we did it. So at a very low current, there is a significant reduction in temperature, and that reduction becomes more and more significant as the current goes up. So for example, at 20 amps current, which is a lot of current, the peak temperature rise was 50 degrees C without the heat pipe, and only about 37 degrees C with the heat pipe. That's a 13 degrees C temperature improvement, which is very nice. Sorry, what? Correct, yes. Yeah, which is not much, right? One advantage of heat pipe cooling is that it is passive in nature. The heat pipe is just sitting there. You don't have to pump the cooling fluid, the working fluid inside it and so on. All you need to do is to blow air outside at the other tip of the heat pipe, which is not very expensive, right? So for that reason, anyway, for that reason, heat pipe cooling is very attractive. Most of the papers in this field have inserted heat pipes between cells. So if I have a large battery pack such as this, I would place heat pipe here, here, here and here around the cells. But the problem is that the rate limiting step lies inside the cell. The thermal conductivity of the cell is so poor that the most difficult step in this journey is thermal conduction within the cell. And that is the motivation for inserting a heat pipe into the cell in order to remove its heat at the very core of the cell. Okay? Any questions? Yes. हाँ, dielectric fluids की thermal conductivity usually कम होती है. See, electrical conduction and thermal conduction usually go hand in hand. A material that does not conduct electricity, like a dielectric fluid, usually also does not conduct heat very well. What? Yes. Because that will conduct electricity. There's a trade-off here, right? You don't want to short your cell. So clearly you cannot use a conducting liquid like water. If you use water, the cell has to be physically separated from the water. There has to be a barrier over which the water flows. It cannot come in direct contact with the cell, right? If you aspire to have the liquid touch the cell, then the non-negotiable requirement is that it should be electrically non-conducting. Uske baad, if it does not conduct heat very well, bad luck, what can you do? In the world of material science, I think this is an open question of designing materials with dissimilar thermal and electrical properties. Can you design a material that does not conduct electricity very well, but conducts heat very well, or vice versa? Those materials can be of a lot of use, not only in cells, but in a wide variety of other engineering systems. Okay? Sorry? Good question. The bus bar and the heat pipe cannot touch each other, because then the electricity will enter the heat pipe and all sorts of bad things will happen. So you have a point. in order to make this all work, you probably also need a hole in the bus bar itself through which the heat pipe can come out, and perhaps some sort of a insulating O-ring in order to prevent contact between the heat pipe and the bus bar. Right? Yes, absolutely. These are all valid practical questions that will need to be addressed if this has to happen in reality. Any other questions or comments here? So, yes.
Instead of drilling into the battery cell, we connect weak pipe just on the top of it, on the edge.
Well,
We just connect our weak pipe on the two ends,
yeah,
and then we can because it's a lengthwise conductivity is too high.
sure, sure.
Can it cool the core?
It will not cool. It will not cool it as well.
But it can reduce
It can. It can potentially do that. Excuse me. One practical problem with that is that the top and the bottom of the cell are already being used for electrical interconnection. So you cannot tell the electrical guys to get out of there and allow you to use the top and bottom only for cooling. If you can share that space, sure. And those are practical questions, those are questions that a company that wants to implement this would have to address.
at lab scale experiment.
At lab scale, it is perhaps useful to show this. My feeling is most people will say, yeah, of course, big deal. What's the novelty of this measurement? We already know that that is how it should happen. Okay? Yes?
So in this case, delta is maximum samples of cell and minimum sample.
Yes.
Suppose somehow we have achieved the delta T less than 5 degrees Celsius.
Yes.
So our objective is control.
Correct.
The delta T should be less than 5. So then we can then why we use our heat pipe at the core?
Well, the heat pipe at the core is what caused you to achieve that. Yes, if I understand your question, if we can get a delta T of less than 5 degrees C using some other means, then you don't need to use a heat pipe. Yes, absolutely. Yeah. The motivation for using the heat pipe was indeed to achieve a delta T of less than 5 degrees C. Within the cell, yes. Core to outside, I wanted that number. See, that number was very large. It was about 14 degrees C, 13 or 14 degrees C. I wanted to bring that number down, and with the heat pipe, we are able to do that.
In general, we don't measure the temperature.
We don't, yes. But that temperature is still important, right? Even if you are not able to measure it, you still need to show through some controlled experiments or through simulations that there is a small temperature gradient inside the cell. Yep. All right. Let me go to the last paper that I wanted to talk about, and that's a fun paper. It had to do with hoverboards. So at some point, hoverboards were very popular in the US, especially among teenagers. So this is what a hoverboard is. It's something that you stand on and you can walk around and rotate and run and all that stuff. You can achieve fairly high speeds on these hoverboards. Does this happen in India? No, not really. Okay. I see that these are available on Amazon anyway. So it's just a device on which you stand and you can walk around like this. I see. Okay. I see. I see. Got it. Got it. It turns out that these have a lithium ion cell in them, a battery pack, a small battery pack in them, which is what provides the wireless energy to move back and forth. And these were notorious at one point for catching fire. There were several accidents around the US of these battery packs catching, these hoverboards catching fire. And they would always catch fire on one side, I think the right hand side not the left hand side. So my student and I, we were interested in understanding what in the world was going on and what we can possibly do to prevent such devices from catching fire. The other thing that was happening was people were falling down and getting hurt, but that was not the problem we were worried about.
But you can feel the gyre underneath your feet. That compensating.
So this was Abhinav Prasad. He did his masters with us, and then he worked for Byton and now Rivian. These are electric vehicle companies, competitors of Tesla, sort of, in the US, designing similar systems for much larger electric vehicles. So the first thing we did was that we purchased a hoverboard like that, and I had to explain to my accounting department why we were buying a hoverboard. And we basically cut it out and basically wanted to understand what it looks like. So it turns out that one half of this hoverboard contains the battery pack, the other half contains other electronics, gyros and all that stuff, which never catch fire. They would always catch fire on the right hand side, the battery pack in particular. So when we open this, we see that there is a computer chip that controls the BMS, battery management system, that controls the battery pack, and the battery pack itself is lying inside a metal casing. So we open the metal casing and we can see the battery pack itself. The batteries themselves are wrapped in a plastic wrap. You can sort of see the greenish batteries right here. There were about 20 individual lithium ion cells inside the battery pack, which together run this thing. And it contains a lot of energy. A heavy human being can stand on it and can walk around for several hours before it completely discharges. So he then carefully took thermocouples and attached a thermocouple to each of the cells that he was able to access. He was not able to attach them to the ones deep inside the battery pack because we didn't want to, break the battery pack. But whatever cells he was able to access, he placed thermocouples on them. And then he did a funny thing. He took a laptop, connected to the data acquisition system, connected to the thermocouples, and he used to just walk around the hallways of the lab, of the building, taking his measurements. So deep in the night, you would see him just walking around, and people would, with a laptop in hand, because we needed to take these measurements while this device is working. Yes, exactly. So that is what he did in the end. He said, this is getting too much and I might fall down and stuff. So he basically created a roller setup. I don't know if we have a picture of it. Yeah, here is a very crude roller. So the hoverboard sits on this roller, and the roller basically rolls, and it sort of mimics the motion of the hoverboard, and we would put some very heavy weights on the hoverboard to mimic a human being standing on it. As you can see, very crude. And this picture, by the way, is very poor quality. Since then we have learned that we need to produce pictures of much better quality. Wires are a big no-no for pictures. It's like a beauty photo shoot. You've got to put makeup, you've got to have the correct lights, right? Everything needs to be right, and then you take a picture. So what we have done is that we purchased a big white board in our lab, a really cheap white, cardboard sort of a thing, and we place it in the back to get a nice background for our pictures. It's an evolution. I look at some of my older papers from 2012 and 13 and I'm like, what was I thinking? And so this allowed us to take measurements of the temperature inside the battery pack as a function of time while the pack is running. And I'll show you those measurements. So I want you to focus on part A first. These are 4 cells, 3, 5, 9 and 7. Let me show you where these cells are. So 3, 5, 3, 5, 9 and 7. These were the ones in which he was able to access and put a thermocouple, right? He could not go deep inside the pack. What happened? He could not go deep inside the pack. So we were limited to measurements only on the outer, sort of the outer cells of the pack. 3, 5, 9 is sort of at the outlet, 7 is at the inlet. And you can see that without cooling or in normal operation, all of these cells have roughly the same temperature and the temperature rise is fairly high. The temperature rise is about 30 Kelvin. So we were already pushing the cells quite a lot. If room temperature is 20 degrees C, they were heating up to 50 degrees C, which is not very far from thermal runaway. I had told him, I think, not to go above 35 degrees C temperature rise under any circumstances. And then we asked ourselves, what can we do to cool these cells? I cannot place liquid cooling or even an air-cooled fan in there. These hoverboards are cheap and there is not a lot of space available, right? So cost is a problem, space is also a problem, right? You saw that video, it's barely enough for one person to stand. I don't have a lot of space to put my fans there and so on. And so he and I came up with what I thought was a very cool approach for this. We said, look, this hoverboard is gonna propel forward in air, right? That is sort of like air blowing over the hoverboard. Right now there is a plastic wrap, a metal casing and another plastic wrap over all of this, which is preventing the air blowing over the hoverboard from actually cooling the cells. Do you see what I'm saying? So deep inside the hoverboard, the cells are there, but the air just blows over the hoverboard and never actually reaches the cells. So we said, why don't we do something very simple? Why don't we cut out holes at the front and behind the battery pack. So this is the outlet grill and there is another similar holes on the other side, basically providing a place for air to enter inside the hoverboard, go over the battery pack and exit from the other side. I don't really need to provide a fan here because the motion of the hoverboard itself provides the flow of air. Right? This hoverboard will never be still, stationary. It's always going to move in air and therefore I will always have the flow of air. All I need to do is to redirect the air to where it needs to be. It was not going where it needed to be. Now with these simple holes in the front and the back, I'm now allowing the air a nice path to blow over the hoverboard. Of course, I have not optimized the internal structure of the hoverboard at all. Right? If I was working for the hoverboard company and if I had the ability to redesign the inside of the hoverboard, I would do much better. I would provide an aerodynamic path for the air to nicely, smoothly go over the battery. But even this very simple thing, this took us perhaps a day to cut out these grills. Even this very simple thing we found improved the thermal performance dramatically. So B is the same 4 cells, temperature rise versus time in the presence of the air cooling situation with those grills cut out in the hoverboard. And you can see that all 4 of them experience a significant temperature reduction. Not all of them cool down to the same extent, but they all do. Yes? In the water? No, the hoverboard will not go in the water. Then it will short something inside and there will be a spark and it will fail. It's not designed to be waterproof at all. It is not designed to be waterproof.
I was just thinking like this hole might decrease the water.
Yeah, it might. So maybe you need some sort of a mesh to prevent the water from going through or something like that, right? If I had control over everything, I would be able to do a lot other things, right? You see the internal structure of the hoverboard was not designed. This entire internal structure was not designed to be friendly to the flow of air. I could do a few things, provide some tunnels or whatever for air to pass through nicely, right? But nobody, I think, had thought about this while designing the hoverboard.
So how did they fix it?
How did who fix it?
Like this company.
I think the hoverboards are not very popular anymore. It was just a teenage fad at that time, and it has sort of died away. It's not that important anymore. But you know, for Abhinav, when he interviewed for an electric vehicle company, they said that look, if this guy can cool 20 cells, then I can trust him to cool 1000 cells or whatever. At least he knows the basics of how do we do this. And so today he is designing much more complicated systems that have real world importance and so on. But even this nice little applied exercise was very helpful for him to understand and for us to also understand some of the basics of heat transfer thermal management here. So as I was saying, we get significant improvement, reduction in the temperature of all 4 cells that we were able to measure. Of course, we don't know if similar improvement happened in the cells deep inside. Perhaps not, because the cells deep inside, the air is still not able to reach them. So it is likely that the cells deep inside the pack are still not being cooled very well by this technique, but we simply don't have the ability to measure those. However, I then asked him to run numerical simulations of the hoverboard. So he created a geometrical model that was as faithful as possible to the actual geometry, and he carried out simulations in which every cell was being discharged at certain rate, and this is free convection, meaning without doing anything, and this is forced convection in which the air is coming from the left and leaving from the right. And you can see that on the same scale of temperature rise, there is significant reduction in the temperature field of the battery pack as a result of cooling. There are still some cells inside that are quite hot, but at least the ones on the outside are being cooled much better than without that little thing. And the beauty of it was we didn't have to provide a fan, a pump, a heat exchanger or anything. The air was already there. All we needed was to provide a pathway for the air to go inside the hoverboard and cool it down. And of course, as you pointed out, waterproof, this, that, there are 20 other practical considerations that need to be accounted for before this becomes mainstream. But nevertheless, from a scientific, perhaps an engineering point of view, here is one way of solving the problem. And you know, because we are sort of researchy, we wanted to compare experimental measurements with simulations, and we saw reasonable agreement between simulations and measurements. Sometimes very good, sometimes not that good, but you know, within the same order of magnitude, following the same trend. And that provided us confidence that the simulation tool can be used in order to design and evaluate different conditions and different configurations and so on and so forth. And actually, to answer your question, we then also said that look, the metal casing around the cells itself was creating a barrier for the flow of heat. And so we ran a simulation, not a measurement, a simulation in which we created holes in the metal casing, and we find that with the metal casing the temperature rises very high. Without any casing at all, if I just remove the casing completely, there is a temperature reduction. But even if you have a perforated casing, that is as good as having no casing at all. In other words, that casing could be, you don't have to remove that casing completely. That casing provides structural stability to the whole system, right? All you need to do is to, punch a bunch of holes in that casing to allow the air to go through. And that itself gets you to very good performance compared to the baseline when you have a metal casing that protects the cells. So this paper sort of is unlike most of our work in the sense that it is very applied in nature, a nice little design exercise, so to speak. But nevertheless, I think we provided some very practical guidelines to the industry about how one could possibly solve such a problem. Okay, we are at 11 o'clock, so we'll stop here and let's take a break of 30 minutes. After that, the last lecture will be light. I'm going to summarize everything that we've learned in this week, and I'm going to offer some concluding remarks. We'll try to keep it short. Thank you so much. All right, let's get started. So, who would have thought that we'll be here for the last lecture of the short course? On Sunday or Monday, it just felt like such a long trip, right? I was thinking about what are all the things I'll teach, and it was just very overwhelming. But slowly and slowly, one by one, I think we've crossed several bridges, and we are here to finish up our short course. I want to summarize everything that we've done in our short course, all the key ideas that I have taught that I hope will stay with you and may benefit you in the future, right? So what have we done in this class, in this short course? I think the two themes, the two keywords that have come up again and again are lithium ion cells and heat transfer. First of all, in my last 10 or 15 years, I have 10 years or so, I have integrated the two. I have studied heat transfer in lithium ion cells. You don't have to do that. You could, in your careers, study heat transfer in something else. Or you could study something else of lithium ion cells. Okay? So please be open to ideas. I have ignited a spark, I hope, in you all, and I hope that that opens you up to new ideas, not necessarily exactly what I taught, but maybe something else, some other ideas that come in your mind as a result of having sat here and thought about this for one intense week, and hopefully that helps you out in your future growth. Okay, today in the next hour or so, what I would like to do is to summarize the key things that we have learned in our class. We started, let's make a list. We looked at fundamentals of heat transfer. We have looked at thermal challenges in batteries. We have talked about heat transfer theory, the mathematics of it. we have talked about experimental measurements. In particular, we've spent a lot of time thinking about thermal runaway as a serious problem, both from a practical point of view and also from a theoretical point of view. How do we predict thermal runaway in a system? One thing that I would like to say there is that we have focused in our lab, and all of the teaching that I did was focused primarily on thermal runaway in lithium-ion cells. But that is not necessarily the only system in which thermal runaway occurs. There could be other systems in which there is a positive feedback loop that causes thermal instability, right? All you need is a positive connection between heat generation and temperature rise. Heat generation causes temperature rise. Is there a mechanism in the system you're thinking about in which temperature rise causes an increase in heat generation? If that happens, that is going to lead the system to thermal runaway. Okay? In the case of lithium-ion batteries, this connection is because of chemical kinetics. Chemical kinetics tells us that reactions happen faster and therefore generate more heat at higher temperatures. There are other systems. I briefly talked about a resistor, a simple example of a resistor. In a resistor, heat generation causes temperature rise, but temperature rise in turn causes an increase in the resistance, which could cause an increase in the I square R heating that happens, right? So even a simple resistor is subject to thermal runaway. It does not undergo thermal runaway in most cases because it is, the increase in resistance with temperature is so small that it is usually a minor effect. But if you look around, I encourage you to think about what other systems, engineering systems, may have this thermal runaway problem. If you can identify a system in which this happens, then I'm confident that the tools that we have developed for thermal runaway in batteries will be easily translatable to other systems in which thermal runaway may occur. Okay, so I want you to keep your minds open about other possibilities, not just lithium-ion batteries. Also, especially to those of you who were not coming into this class familiar with heat transfer, I hope I have introduced you to some fundamentals of heat transfer. Heat transfer is such an omnipresent phenomena that you can find interesting problems to solve almost anywhere you look, right? Almost everything we do as human beings, as a society, involves heat transfer. Cooling of buildings, cooling of cell phones, human bodies, the human body itself involves a lot of interesting heat transfer problems. A lot of therapy, cancer therapy, cryotherapy, etc. happens on the basis of heat transfer. I have a personal story to tell there. I had a little something in my back that was causing me some trouble, and the doctor said it was some growth on my bone inside. So the doctor said, okay, we will drill a little hole in your back and we'll basically zap it with some heat. As soon as he said heat, I said, interesting. So this is a true story. First of all, this little operation happened on my birthday. So I was lying down on the operating table, and just before they cut you open, they have to confirm for the last time that you are who you are supposed to be, right? So they asked me, what is your name? What is your date of birth? I told them my date of birth. It was the day of the operation. They said, and the doctor was a little funny. He said, now we are going to cut the birthday cake. And so what they did was that they drilled, they basically cut a small hole in the back, and then they took an electrode and they inserted it inside until the tip of the electrode was touching the bone where the problem was. And once it touched the bone is when they passed a bunch of current through the tip of the electrode, generated a bunch of heat, right, and basically zapped the little whatever that was causing trouble. And then he said, we have to wait for a little bit of time for the heat to propagate so that it completely zaps, and then he takes it out. And throughout all this time, I was still conscious and I was thinking about all the concepts of heat transfer that apply to this problem. Okay, the point I'm trying to make is that problems related to heat transfer occur everywhere. Everywhere you look, there is an interesting heat transfer problem sitting there waiting for you to solve. So I want you to keep your eyes and minds open. I know as PhD students, you're interested in new ideas, new thoughts, new problem definitions. And so I'm telling you that heat transfer in particular is a very open, rich field in which to solve such problems. Anything and everything that is happening around us, you know, energy, renewable energy, electric cars, climate change, etc., new materials, these are all things that involve heat transfer. So who knows, perhaps if you're looking for a good problem for your next project, who knows, that problem might be related to heat transfer. Okay. The other thing I would say is that the theory, the mathematical theory of heat transfer is also very rich. I have only scratched the very surface of this very rich mathematical field. There is a lot more mathematics that goes inside heat transfer theory. Everything that I talked in this class was mostly about thermal conduction, but there is also convective heat transfer and radiative heat transfer. And so perhaps if you are mathematically inclined, then looking at the mathematics of heat transfer theory is also one direction in which you can possibly go. Okay. Experimental measurements is also an interesting and important topic. I talked about this in the context of lithium ion cells, but a lot of the principles that I have taught here are very universal. The concepts of repeatability, the idea of uncertainty, the importance of calibration, and in general, the importance of thinking about experiments and not necessarily doing. In most cases, the experiment itself, the act of taking a measurement, is not very difficult. You can always easily measure, right? However, you have to think much in advance about how you're going to do that measurement, how you're going to ensure that whatever you measure is indeed reliable and repeatable and has low uncertainty and all the other good stuff. Okay. We also, by the way, here I will put here the lecture yesterday about technical communication. It was not a technical talk, but nevertheless it's extremely important, right? No matter what you do, you will be communicating your results through either written or oral means, and the quality of that communication ultimately determines what you get out of it, right? As I said, nobody is going to go to your lab and look at your setup. They will look at the picture of the setup that you show them in your presentation. And if that picture does not do justice to the hard work that you've done in your setup, then you are the one that loses. Yeah. So make sure that you do good work. I'm not prescribing a way to short circuit the importance of hard work, right? I'm not saying don't do anything, just make a good presentation. That's not the idea. What I'm saying is work hard in the lab, but then don't ignore the importance of being able to present it equally well. And remember, in both of my presentations yesterday, the one thing that I said again and again is the importance of practice. I'll say it one more time. Nobody is born with any innate skills as a presenter or as a writer. All of us get better and better at it with practice. The more you present, the more you write, the better you will get at it. So whenever there is an opportunity to present your work, raise your hand and be the first one to volunteer to give a presentation. Ask your advisor to get you involved more and more in the writing process. Write yourself, write every week. Every week, write 2 pages about your progress in research that week. That itself will help you generate more ideas. You know, when you write, you're actually thinking, your mind is thinking about the work. Your mind will think about the next steps, what went wrong, what might be done to fix what went wrong, what should I be doing next, how should I be fixing my problems, etc. These ideas come when your mind is engaged in the act of writing. So I would strongly recommend you all to think about technical communication almost as much as you think about the technical matter itself. Okay? Some of the things specifically with lithium ion cells that we have looked at is the idea of internal thermal resistance of the cell and external resistance of the cell. So this is our internal and this is our external. Our internal has to do with the material of the cell, the thermal conductivity of the cell. And I've shown through simulations, experiments, etc., that usually the internal resistance of the cell is the dominant step. It's the rate limiting step. I can easily cool the cell down at the bottom, sorry, on the outside. And again, these are thermal resistances, folks, not electrical. I can easily make the external resistance as small as possible by blowing a bunch of air on it, liquid cooling, all that stuff. Usually it turns out that the internal resistance of the cell becomes a problem. And that is something that I don't have much control over necessarily. I can't blow more air over it and change the thermal conductivity of the cell. The thermal conductivity of the cell is a function of what is inside of it, how it is organized, and so on. And so there is a great need for innovations in materials science. There is a need to come up with better and better battery materials. And right now, that need is being driven by a search for better electrochemical materials. Materials which will charge and discharge faster, which will store more energy per kilogram, etc., etc. In my opinion, there is not sufficient work out there on understanding the thermal performance of such materials, right? That approach is completely justified. If you're looking for a better battery material, it needs to store energy, right? That should be the primary metric. But once you figured out that there is this material that can store energy very well, then secondarily, you must then worry about its capability to remove heat. So at some point in time, thermal engineers would have to start worrying about the thermal properties of all these new materials, these new battery chemistries that people are looking at. And I feel that a good collaboration between thermal engineers and material scientists can be very fruitful. So material scientists know a lot about the lithium intercalation and the materials that go inside of it and how lithium, diffuses and all that stuff. So, the focus of our class was on lithium ion batteries, but quite likely in the next 10 years, lithium ion technology will be overtaken by some other technology like sodium ion or potassium ion or whatever it be. It will bring its own set of challenges with it. And I want you as a thermal engineer to be ready for those challenges. Now that you know what the challenges in lithium ion cells are, quite likely the next generation technology will also offer some similar challenges and maybe some new challenges. I hope we all are ready to take up those challenges and to make contributions, for the next 20, 30, 40 years as your careers probably are going along. Okay? I have said at the very start of our class that lithium ion cells are a very multi-scale system. By the way, before I start talking about this, I do want to emphasize the importance of collaboration once again. None of us can do everything together. It is very important to extend a hand and create a connection with somebody else who has a synergistic expertise as you. And oftentimes it just boils down to making that initial connection, making that initial contact. So please never hesitate to go talk to somebody who you think can help you in your work. Trust me, people are always willing to listen. People are always welcoming new ideas, and somebody else, perhaps a material scientist, is also looking for a thermal engineer who can help them in their work, right? We all tend to work in our silos, unaware of each other, but if you make that initial contact, such collaborations are extremely fruitful. I know it can be a bit of a, you can be a little hesitant to do that, to sort of introduce yourself out of the blue and all that, but do that, and trust me, these things lead to very good results. Within your institution, in other departments, if you go to a conference and meet other people, introduce yourself, tell them what you do and figure out what they do. And some of the connections I have made, in informal settings like dinners and lunches and so on, are the ones that have brought me a great deal of success in terms of research. Okay, so I would encourage you to do that. I have said that lithium-ion cells are a multi-scale system, starting from atoms and molecules to components such as electrodes, anode and cathode, etc., to individual cells and to packs. You can perhaps find your niche anywhere in this scale, right? And this is a very large scale. Atoms and molecules perhaps at the scale of 10 to the power 9 meters, all the way. Large battery packs can be as large as 10 to the power 1 meter. Large battery packs, right? Depending on your training, your expertise and your interest, you can perhaps find an interesting problem to solve anywhere in this range. And the tools that you will use depends on the scale, right? Perhaps you're interested in using ANSYS as a simulation tool, in which case you will probably be somewhere here. You want to understand what happens to heat transfer in a large battery pack as it heats up and cools down. One important problem that we did not talk about in our class at all is that of fire. What happens when a battery pack catches fire? How does that fire spread? How do you extinguish that fire? And how do you prevent such fire in the first place? So one of my students, Dhananjay Mishra, I didn't get to talk about his research too much, but he spent a PhD looking at simulations of thermal runaway in battery packs. He now works for General Motors in Detroit, and the problem that he works on is actually very simple and almost silly. He says that General Motors is going to use tens of thousands of batteries in their electric cars. They're going to have to buy these batteries from somebody and they're going to have to store them somewhere. So imagine a big warehouse, bigger than perhaps this building, where they have stored hundreds of thousands of cells ready to be used, integrated into their cars, right? What happens if there is a small fire in this warehouse? It's like storing this much petrol in one place, right? How do you prevent fires in a place like this? How do you place fire extinguishers in optimal locations? Imagine if I have this room full of batteries, what would be the right locations to place fire extinguishers? There are these things, bunch of water will come out and extinguish the fire. Is water even the right liquid for preventing battery fires, for managing battery fires? And suppose it is, then where do you place them? You see, do you place them at the top? Do you place them on the walls? Or do you place them on the ceilings? Those are the kinds of questions, very practical questions that he's trying to answer. He says, they move their battery packs using forklifts. You know what a forklift is, right? Suppose the forklift operator is negligent and he or she runs the forklift into a battery pack, into a bunch of battery packs, and they fall down on the ground. The very act of the battery falling down on the ground may rupture it and cause a thermal runaway event. So you can imagine there are all kinds of practical problems that storage and use of battery packs can cause. Can you come up with some interesting question that you want to answer in that regime? One problem that one of my students and I are just beginning to work on is the problem of cargo transportation of lithium-ion cells. So imagine if you have to transport a large number of cells and you put them in the cargo hold of a plane, then that can be very dangerous, right? Because any small malfunction there can cause a fire and then you have to figure out how to fight that fire. All cargo holds in a plane are equipped with some fire extinguishers that are designed to start as soon as there is a fire. But an open question is, are those fire extinguishers appropriate for battery fires or not? And if they are not, then what do you do about it? You cannot possibly go to every plane and change the fire extinguishing mechanism in all planes, right? How do you use the system that you already have in the best possible manner in order to do what you want to do, right? Those are the kinds of questions that we are trying to answer right now. Question?
So the last time when you were given the seminar, you were discussing about that simulation in which you have simulated thermal and everything.
Yes, correct. Yes, absolutely. I had given a virtual seminar at IIT Ropar 3 years ago, 2 years ago, something like that, in which I had discussed that aspect of the work in detail. I didn't talk about this in this short course mainly because I didn't want to repeat. Anything else? Okay, cool. Yes. Yes. Well, the parameters we study are, firstly, if this is a cargo hold and I have pallets of batteries, then how far should these pallets be placed? What should be the gap between these pallets so that if one of the pallets catches fire, the fire does not spread to the next pallet? Strictly speaking, if I keep my pallets far enough, then the fire will not jump from one to the other. But then what that will mean is that I will only be sending 2 pallets in a plane when I could have sent 10. You know what I'm saying? But if I keep them too close to each other, then the fire is going to spread very easily. So we do simulations in which we try to understand what is the minimum distance between pallets in order to prevent such fires. Particularly in the case of cargo planes, one interesting challenge is that the temperature up there is very different from the temperature on the ground. Typically it's very cold up there at the heights that the plane travels at, and the pressure is also very low. The cargo hold is not pressurized, so the batteries are seeing very low pressure ambient, and that's a problem because inside the battery there is very high pressure. Now outside, if the pressure is low, then there is a lot of stress on the walls of the batteries, and any little thing can cause rupture. So one question is it acceptable to transport batteries in a low pressure cabin, in a low pressure cargo compartment, or do you need to transport it, do you need to pressurize the cargo compartment or not? Does that make sense? Cool. So I think fire is an important thing that we really didn't talk about too much in our class here, but nevertheless is a very important topic. It's also a very practical question. If there is a battery fire, if an electric car catches fire on the highway and the firefighters come, they need to know how do they handle this fire. Do they pour sand on it? Do they pour water on it, or what? There have been accidents in the US where an electric car, hits something, catches fire, the firefighters come, they extinguish the fire and they go away, and 2 hours later it catches fire again somehow. There is a term for it, reignition or something like that, and people don't quite know why that happens and what you can do to prevent reignition from happening. There are all kinds of open questions related to battery fires. Personally, I am very interested and excited about the theoretical ramifications of thermal runaway. The idea of thermal instability. Like I have said, instability is a phenomena which is very well studied in mechanical vibrations, in fluid mechanics, and so on. We know when a mechanical system can become unstable, right? Resonant frequency and all those concepts. We know when a fluid system can become unstable and lead to turbulence and so on, right? The understanding of instability in the context of heat transfer is not as well known, and therefore I think there remains work to be done in the area of instability in the context of lithium ion cells. So can we come up with better strategies to predict thermal runaway in advance is the main motivation driving that theoretical work. You see, if I have a battery pack and if it starts undergoing thermal runaway, then it is already too late for me to do anything about it, because those chemical reactions have already started. They are going to generate heat. Even if I somehow start cooling them, that heat will cause the next set of reactions to occur, and very soon the entire battery pack will catch fire. It's like having a room full of some volatile gas, like cooking gas. If I light a matchstick and if that explosion starts, it is already too late for me to do something about it, right? I need to prevent thermal runaway much ahead in advance and not wait for the event to actually have started already. So proactive prediction and prevention of thermal runaway, I think is a very important topic. Prediction and prevention of thermal runaway, I think is a very important topic, both from an applied point of view. If I give you a battery pack, can you run some experiments or some simulations to predict the limits up to which you can take this battery pack before it becomes dangerous, right? And also from a theoretical point of view, forget about an actual battery pack. Suppose you have a thermal system and you want to do some applied mathematics, then that also is a very rich field in which to do some good work. Can you come up with the next non-dimensional number that will predict the occurrence of thermal runaway and so on and so forth? So I feel, and I'm having seen this, I'm very passionate about this. I feel that there are some very interesting theoretical problems as well as applied problems for us to solve in this field. Okay, any questions or comments yet? The other thing I would like to say is that heat transfer in lithium ion cells, but also in general, is usually very highly coupled with some other phenomena. Usually heat transfer does not occur only on its own. In the case of lithium ion batteries, the other physical process that happens along with heat transfer is electrochemistry. We learned a great deal from Professor Agrawal's 2 seminars on electrochemical modeling of lithium ion cells, and that is important because the heat generated in a cell, which makes us worry about all the other things that we have worried about, happens because of electrochemical reactions, right? So this in some sense is the root of the problem. If I want to truly understand heat transfer, I really need to start learning electrochemistry. My students and I have learned a little bit of electrochemistry as we go. Of course, there are other experts who have built careers out of electrochemistry, and sometimes we talk to them and we get their help. One way or the other, we never say, oh, I am a heat transfer engineer, don't ask me about electrochemistry, right? That's not the right approach. The right approach is to say, okay, I'm a heat transfer engineer, the system I am studying involves electrochemistry, I need to teach myself enough electrochemistry, or I need to shake hands with someone who knows enough electrochemistry in order to solve the problems that I'm wanting to solve. So my other advice to all of you is to be open to new fields and new areas in your careers. In the 30 or 40 years of careers ahead of all of you, it is quite likely that you will not be doing the same thing that you're doing today. It is quite likely that you will perhaps not even be in the same department that you are in today. It is possible that 20 years later you will not even be doing engineering. at all. You might be doing something entirely different, right? There's only a few of us, myself included, who stick to something that they learned 25 years ago, okay? So 25 plus years ago, I was sitting in a room, taking a class in thermodynamics, and something inside me said, wow, this is so cool. And I have the privilege of being able to do the same thing even 25 years later, okay? Somebody might call it very boring, and I can understand that, all right? To each their own. Perhaps you will stick to what you're doing and do it for a long time, but quite likely, in the majority of cases, you will be looking at other things, other systems in the near future, in the next 5 years, 10 years, 15 years. And the one very important thing is to be a lifelong learner. Be open to stepping outside your comfort zone. We all have a comfort zone. I know heat transfer very well, and I'm very comfortable solving heat transfer problems, right? It takes an effort to step out of your comfort box and start learning about new areas, new fields. And it takes time, it takes a lot of patience, but it is something that I think is extremely important to do, right? So please be open to being a lifelong learner. You never know what direction your next opportunities will come from. You have to be open to such new opportunities, and don't ever be a thermal engineer forever. And this is especially true if you're going to go and work in the industry. If you're going to finish your master's or your PhD and go work in a company, then you will find there that nobody is a mechanical engineer, nobody is a thermal engineer. Everybody, by definition, engineers are problem solvers. Whether those problems come from your area of expertise or other areas of expertise, you're responsible for solving those problems. So go figure out how to solve problems. And in some sense, doing a master's or a PhD is teaching you, exposing you to difficult problems and challenging you to solve those difficult problems. Once you have solved some difficult problems successfully in a PhD or a master's, I feel that you are now ready to take up any other problem in the world and solve it confidently. The point I'm trying to make is that the problems in the future may or may not come from the same area in which you are working. Okay? I also want to say that there are a number of open problems at the intersection between heat transfer and electrochemistry. For the precise reason that people are not comfortable stepping outside their zones. Heat transfer people have done a lot of heat transfer analysis of cells. Electrochemists have done a lot of good electrochemical analysis of cells. What is lacking is somebody at the intersection between heat transfer and electrochemistry to be able to integrate the two in one shot. So thermal electrochemical modeling, thermal electrochemical modeling is a topic of a lot of current interest right now. Remember, for example, the heat transfer modeling that we did, we said k d2t by dx2 plus q of t is equal to rho cp dt over dt. And as an approximation, we simply said q of t is equal to beta times t. Q of t is the heat generation that occurs because of electrochemical reactions. And I made a very gross simplification that all the electrochemistry that is happening is being bunched together into this parameter beta. And I'm assuming I know the value of beta, right? That may be a reasonable way to start, but certainly requires more sophistication. This beta comes from electrochemistry. On the other hand, when electrochemists solve these problems, like the equations that Dr. Agrawal had presented, I forget the exact formulation of those equations, but roughly speaking, Fick's law, yep. Del by del x of d dc dx plus blah 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 equals something else. He wrote all those equations assuming that the temperature is the same everywhere. He assumed isothermal conditions, because of which his diffusion constant was a constant. It was not a function of temperature.
It was not, when multi-deriving, it is not a constant. We can keep it as a function of temperature also.
We can do that, but that significantly complicates the calculations, right? So the point I'm trying to make is that the thermal model, strictly speaking, does not stand by itself. It is dependent on the electrochemical model, and similarly the electrochemical model itself is dependent on the thermal model. You need to solve the thermal field to be able to know your D, so that you can solve the concentration field. And only after you can solve the concentration field will you know how much heat is being generated, which goes as an input into this equation. So it's sort of like a chicken and an egg problem. There cannot be an egg without the chicken, but then there can also not be a chicken without the egg, right? So which came first? My approach is they both should come together.
When we couple it, it is like that only.
Exactly.
The output of electrochemical model will be the input for
And vice versa.
and this loop will
This loop will keep going on and on, absolutely. There is a need for us to come up with better integration between thermal models and electrochemical models at the scale of atoms and molecules, at the scale of anodes and cathodes, at the scale of individual cells, and also at the scale of large battery packs. In this class, our discussion of stuff that happens at the scale of atoms and molecules was very limited. Right here, I only very briefly discussed molecular dynamics simulations. At the scale of atoms and molecules, MD simulations is a very commonly used tool for both heat transfer and electrochemistry. So if you would like, I mean, it's not trivial. It's not something that you can learn in a day or so. It does take a significant amount of effort and commitment. But if you can teach yourself molecular dynamics simulations, then there is really not a lot of people working on MD simulations for lithium ion cells. There's an army of people doing MD simulations for all kinds of things under the sun, right? But can you learn enough MD simulations and create a niche for yourself by applying MD simulations for solving some interesting lithium ion cells related problems? Nothing that I'm talking about here is trivial, right? I'm not giving you a key that go and tomorrow you will have enough ideas to do your PhD. Each of the thoughts that I'm trying to ignite in you will take some effort, and it's quite possible that you think about something for a while and then decide, look, this is simply not feasible for me. I am simply trying to start a thought process in you all, a conscious thought process to think about what are the right things for me to work on. And trust me, believe me, having done a PhD myself and having seen several PhD students in my lab, this is the most difficult part of doing a PhD or a master's, right? Identifying the problem statement, what it is that you want to do. Once the problem statement has been identified well, then solving that problem itself is not that difficult, right? You all have taken so many classes, will take several classes that teach you the tools, right? You can take a semester-long class in MD simulations. It will teach you the tools to solve problems. It will not tell you what problem to solve, right? That is up to you. That is for you to read the literature, read review papers, good quality review papers, and get an understanding of what are good problems to solve in this field, using the tools that I have learned or using the tools that I can learn. You may not know MD simulations today, but if you find that I really want to do MD simulations for lithium ion cells, next semester you can sign up for a class on molecular dynamics simulations, either here at Ropar in person or online, right? These days the Possibilities are limitless. You teach yourself MD simulations by whichever way you need to, and you are then ready to solve problems related to lithium ion cells. I am myself not an expert in this field, but I feel that this is a very good topic for you, for anyone to make some good fundamental contributions in. And the good thing about it is that as with an expertise in MD simulations, you're ready to solve all kinds of problems in the world, not just lithium ion cells, but who knows what in the future. Solar cells, energy conversion, God knows what in the future. Okay, any questions or comments so far? All right, what else do I want to say here? Let's see, let's go back to the original, the first slide. Let me say a few things about experimental measurements as well. Everything that I've taught here applies very generally, right? So experimental measurements is something that many of you will probably be doing for your PhDs. It may not be measurement of temperature, it may be measurement of something else. But some of the principles that I have taught in this class in the context of temperature measurement for lithium ion cells applies in a very general framework. Anytime that you want to measure something, you have to think very carefully about how you're going to measure it. Please don't jump into the fire right away. Think about what you're going to do, how you're going to do, what is the best way of doing it, how do you ensure that you have confidence in your measurements and so on. And only when you think you're ready is when you are ready to jump in. Okay? Create a team around yourself. Have somebody, some trusted person you can talk to and bounce your ideas around. Talk to your advisor certainly, but also somebody else, maybe a lab mate or something like that, who can help you refine some of these ideas, right? Experimental measurements are beautiful. Once you have a good system in which you are able to take good measurements, it looks very good to get experimental data, but it does take quite a lot of effort to get there. You have to worry about what equipment you will need, what consumables you will need, and of course you may have to order some and it takes time for it to come around. And during that waiting time, I hope you're thinking that, look, when my instrument is here, what am I going to do with it? What will my strategy for measurements look like? What will I measure? How will I measure? How much will I measure? How many times will I measure? How will I analyze all that data? What will I do with all that data? What are some good questions to ask with that experimental setup? For example, the immersion cooling setup, Swapnil's immersion cooling setup that we talked about, had a bunch of cells immersed in a coolant with a bunch of temperature sensors, pressure transducers, and the ability to pump fluid back and forth through the system, right? Having created a simple system, well, I wouldn't call it a simple, but having done the hard work to create this system, now is the time to think creatively about all the cool things that you can do with this, right? Brainstorming is extremely important. What kinds of questions can you ask from this system? Question number 1, can immersion cooling prevent thermal runaway? That's probably a question that I want to answer at the very end, because cells may explode and I will not have my setup again, right? So only after I have asked a bunch of other questions, published 2 or 3 papers, will I commit to the risk that things might blow up. Yeah, and of course your personal safety and the safety of the lab, etc. is important. So you need to think about all that. One thing that we had learned was that this cell gets very cool, but this cell remains hot because of the direction in which the coolant goes. A very simple way of solving that problem is to periodically change the direction of the flow of the coolant. So this pump that you have outside sort of becomes a two-way pump. I can pump in this direction, and when I want, I can start pumping in the opposite direction to sort of make it equal for all cells. If I do that, how frequently should I change the direction of the flow is an interesting question. You see, I'm a firm believer that once you start thinking about a system very hard, you stare at that system enough, you can and you will come up with all kinds of interesting questions to ask. Yes.
Like I was also having the same question. Maybe will flow that. There will be some point that the temperature gradients will reflect inside the stack.
Yes, absolutely.
And to remove, we can use some different type of configurations into it.
Yes. I want you to be creative. I want you to be, the possibilities are endless, right? Who is stopping you from creating multiple inlets and multiple outlets, right? Oops. I don't want you to do that. What if I have multiple inlets and outlets? So this is an inlet, this is an outlet, this is an inlet or outlet or whatever have you. What are the best places to place, what are the best locations in your rig to place these inlets and outlets? How will you answer that question? One way to answer that question is to place a large number of inlets and outlets and plug them up. Run experiments in which you open this one, close this, then close this, open this, close that, open that, etc., etc. You can play a beautiful jigsaw game, right? Once this experimental setup is there. So once you worked hard to set something up, don't let it go easily, right? It's like, I don't know what it's like, but once you have caught this in your, once this is in your hands, look at it this way, look at it that way, right? Don't let go of it until you have exhausted all possible questions that you can think of. Okay? Any other interesting things that we can do here? Thermal runaway we said, directionality of flow we said.
One more to remember, the spacing between the cells.
Yes.
Approximately 1 mm.
Yeah, something of that order.
Because I haven't seen it with with myself. They are using a paste, one paste type of thing, to just stick it, and that to approximately 1 mm.
Right.
And in between that, to provide each and every type of cooling.
Yes.
Like we are sitting in it, we will have space and all.
Yes.
The visual impression that it is having that way. But if you draw on the cells, it will, we will just like coinciding or touching.
Almost, yes. Almost coinciding, yes.
In that scenario, if we try to do all anything, what?
Good question. I don't know the answer to that. How does this fairly viscous fluid penetrate into the nooks and crannies of the battery pack? I would like to go back and ask the question of why the cell to cell gap is only 1 mm in the first place. Can we make it 2 mm? Maybe the original choice was arbitrary. Maybe they said, I just want to get them very close, so let's make it 1 mm. Maybe if you keep them 2 mm apart, it really won't hurt the spacing, the size too much. But the change in gap from 1 mm to 2 mm, from a heat transfer point of view, can significantly improve heat removal. Maybe.
I ask a similar thing.
Yes.
When we think about the small module, then this thing is done. But when we think about a whole battery pack,
Sure.
if we increases the 1 mm gap,
it adds up.
It will create a huge difference between the whole total battery capacity.
Sure,
Because
absolutely.
the one line can be removed.
Sure. So you have to come up with what is the optimal spacing there. Maybe not 2 mm, but maybe 1.5 mm will give you a reasonable compromise between the two. I don't know the answer to it. I'm forcing you to ask questions. It's up to you to find the answers. And the answer to this question can probably come from a combined approach between experiments and simulations. It's very difficult to run these measurements at 1 mm, 1.5 mm, 2 mm, etc. Right? Changing the size of the gap between cells is not trivial. But you can, just like Swapnil did, create a numerical simulation in which it is much easier to change the gap, run a new simulation and see what your simulations will predict. When you do have numerical simulations, I think it is very important to have validation. Anybody and their uncle can create a numerical simulation and get some results out and show it to the audience, right? How do you believe those results? That validation, I think, is extremely important. In order to show a good, tight PhD dissertation that people can believe in, it is important to take results from numerical simulations and compare them with experimental data. That experimental data doesn't have to be yours. It could possibly be somebody else's experimental data reported in the past, right? That is quite acceptable. In fact, when we write a manuscript, a paper, it looks very good when you're comparing your results with results from somebody else. When the two are in good agreement with each other is when there is good confidence in those measurements. Okay? So we are at 12:30. I will stop here. I hope the GIAN course was helpful and useful to you all. Please stay in touch. You have my email address. Even several years later, I would be interested in learning about where you are, how you got there, are you still working on batteries, and whether what you learned here in the GIAN course in some little manner helped you in your careers. All right. So with that, I'll thank you all. It's been a pleasure. Thank you, Himanshu ji and Kulbhushan ji, for all the facilitation. As you can see, he's doing double duty. He's trying to learn, and at the same time, he's pushing paperwork here and there. So he's done some very good, excellent work. And so with that,